This video is going to introduce double replacement reactions. And the best way of describing a double replacement reaction is it's like double dating. And I often use the analogy that, let's say we have prom happening and you head to the prom with a date that you're kind of attracted to, and then another friend goes to the prom with another date that they're kind of attracted to, and yet when all of you come together, you switch dates because there's a much greater attraction. And so it's sort of like double dating that's gone wrong, where everyone comes home with a different date than what they started with. Let me describe that in a little bit more detail. So let's say, for example, if I have a chemical where I have A and B being the cation and anion that are together, and then C and D being the other cation and anion together. Here we are in the case of, here's one couple, there's another couple. They head into the chemical reaction, and what happens is that A lets B go and attaches onto D, and where C lets D go, it attaches onto B. And so they are literally replaced twice, hence why it's called double replacement. So when we do that, if you can include in your notes, the first thing we need to do is separate the reactants ions, just to see what ions we have. And then we're going to switch them. We're going to recombine the ions, remembering that anions, which are negatively charged, are attracted to cations, which are positively charged. And we essentially switch them. Make certain that each new chemical has noble gas configuration. In other words, it needs to have as many ions so that it gains, that it can have a full valence shell, or that the other ion has lost all of its electrons. And then the last step is balancing the chemical equation. So let's go through an example, a couple of examples, and then I'll have you try it on your own. So here we have lithium sulfide and silver nitrate. Okay, so we'll start off with recognizing which ones are the cations and which ones are the anions. So I'm going to go ahead and draw lithium with its two lithiums, with each having one valence shell. And then if I look at sulfur, I'm going to put sulfur as a blue chemical. The reason I'm using blue is that because lithium is a cation and sulfur is an anion. There we go. And we know that the reason that sulfur requires two lithiums is because of it having 6 valence shells, and it wants to get 2 more, and that lithium can only lose 1. So there we have that. In the next reactant, we see that we have silver. Silver, remember, always has a positive charge. Let me make sure that that's in red then. There we have our silver with a positive 1 charge, and it has is attached to with nitrate. Nitrate is a -1 charge. That means it has 7 valence electrons. There we have our nitrate. There we go. So 1, 2, 3, 4, 5, 6, 7. So just as a reminder, we have the anions, which are negative charged, in blue, and I have my cations, which are positively charged, in red. And we just reminder, cations, positives, are attracted to negatives. All right, so let me just go ahead and draw over here the fact that we only needed 1 because nitrate has 7 valence electrons. Okay, so now we talked about, this is the point where now a double date happens. Lithium and sulfur, they're attracted to each other. Silver and nitrate, they're attracted to each other. The attraction isn't as strong as it could be. So in this sense, if these all came together, if we more or less combine these, and now they have a new set of cations and anions they can date, what is lithium going to be attracted to? Well, lithium, being positive, is going to be attracted to the negative. So lithium is going to be attracted to the nitrate. Remember, we're switching these cations and anions in a double replacement. And as you notice, it only takes one lithium. We'll go ahead and paint that on there. It only takes one lithium for nitrate to get its 8 valence electrons, and it only takes one, and lithium just wants to lose 1 electron. So we're going to just keep it like that. Don't worry that there's a second lithium until a little bit later on, okay? Now what we're going to do is we're going to take a look at silver. Is silver going to be attracted to a different chemical? And the answer is yes. Of course, it's going to be attracted to an anion. Remember, it has 1 valence electron. So the other anion that we've got is the sulfur. And in this case, sulfur, remember, has 6 valence electrons because of that -2 charge. And what we're going to be doing is, you'll notice that silver can provide 1 electron to sulfur, but that sulfur still needs another electron, and so we're going to give it another silver. Don't worry that we don't have a silver on the other side. We'll deal with that later on. All right, so at this point, we recognize that we have lithium nitrate. Remember, we swapped, the red swaps its dates with the blue, and it looks like lithium needs simply 1 nitrate to be content. I look at my solubility chart and I see that these are aqueous. Okay, now let's take a look at silver and sulfur. So it looks like I need to have 2 silvers for every 1 sulfur, and this one here I believe is a solid. Okay, so now in all of this here, we made sure that everything, every chemical has its full valence shell. But the problem is remember, what you start with, you end with. We're just rearranging things. So is there a way that we can balance this chemical equation? In other words, what we start with, we need to end with. Well, we always start with the metals. So let's go ahead and start with the metal. If I have 2 lithiums here, I need to have 2 lithiums there, but I can't just draw a lithium. I need to draw lithium nitrate, the whole chemical. So I'm going to add another lithium nitrate. Remembering, the step I'm doing now is balancing the chemical equation. So here is my nitrate. We have 7 valence electrons. 1 of them goes here. Okay, so that balanced out the lithium, so that's good. Let's look at the next metal. For the next metal, it says that we have 1 silver here, but 2 here. So let's go ahead and add another silver on the reactant side. Let's see what color I have right here. Make sure it's in red. There we go, Ag. And then I'm going to add my nitrate. Remember, you can't just add a silver, you have to add the whole shebang. There we go. And well done. All right, so now we have 2 silvers on the left-hand side, 2 silvers on the right-hand side, 2 lithiums on the left, 2 lithiums on the right. I also remember the next thing I want to do is look at the polyatomic. I have 2 nitrates on the left. Oh, look at that. I have 2 nitrates on the right. Brilliant. 1 sulfur on each side. So now let's do a count. it looks like I had one lithium sulfide, but then I have two sets of silver nitrate. So I'm going to put a big 2 in front, showing that I have two sets of them. In other words, 1 mole of lithium sulfide plus 2 moles of AgNO3. And now I take a look over here. I have a big 2 in front here because I have 2 lithium nitrates and 1 silver sulfide. So at this point, I've now created a double replacement reaction that is balanced. Let's try one more. Okay, so same sort of setup. We'll go ahead and start by drawing our barium hydroxide, barium having 2 valence electrons. And I'm going to make my life easier and already draw my hydrogen so I don't have to switch pen colors. Okay, hydroxide, remember, is an O and an H. I look at my polyatomic chart. It has 7 valence electrons. That makes that hydroxide have its full valence shell. And there's the next one. Okay, so now with that said, let's work on hydrogen and chlorine, and we call this hydrochloric acid. Don't have to worry about the name. Remember, chlorine has 7 valence electrons, and it just takes 1 hydrogen for 1 chlorine. All right, so now again, that double date happens. Barium hydroxide and hydrochloric acid, or HCl, come to the dance. Barium wants to find a new date, as does hydrogen. And barium's new date is now chlorine. So we need to make certain, remember, that positives are attracted to negatives, or in other words, whichever wants to lose electrons is attracted to what's going to gain electrons. And barium, remember, has 2 valence electrons. I'll go ahead and draw the hydrogen too. Now let's do our anions. We have chlorine now being the new date. But you'll notice that barium wants to lose 2 electrons and chlorine only can take 1. So in that case, we're going to have to give this barium 2 chlorines. Don't worry that we don't start with 2 chlorines over here. And then let's work with hydrogen. Hydrogen is going to now be attracted to OH. Remember, that has 7 valence electrons, and there we go. We now can have hydrogen give its 1 electron, and that will allow the hydroxide to get all 8. So for this one here, let's make sure that what we started with is what we ended with. We have 1 barium. We always start with our metal, and 1 barium here. So that looks good. All right, now let's start with polyatomics. That was the next one. We have 2 OHs here. We need to have 2 OHs here. What that means is that I need to add another HOH. Okay, so I'm going to put an H over here, and then that allows me to get another hydroxide. Perfect. Okay, so far we have our OHs being equal, all right, but we don't have, now the next step is getting anything else that's not hydrogen, carbon, or oxygen. So let's take a look at our chlorines. I have 2 chlorines here, but I only have 1 chlorine here. So in that case, I'm going to have to give this another HCl. Okay, and it works out beautifully. Let's double check that we have everything being what we started with, what we ended with. We have 1 barium here, 1 here. We have 2 OHs on the left, 2 OHs on the right. Then we look at the chlorines. Remember, hydrogen is last. We have 2 chlorines here. We have 2 chlorines on the left-hand side, and we happen now to have 2 hydrogens. So let's write down what our chemical equations are. We have one barium hydroxide, so we leave that blank, but we have two HCs. Now let's write this chemical formula. We have BaCl2. Remember, this small 2 tells you how many you have attached to it, and I believe that that is aqueous. And then I have, at this point, HOH, which has the big 2, or we can also call that H2O. So we can have 2H2O. This is what we call an acid-base reaction. Those are typical for double replacements. So whenever you have an HOH, make it water. Whenever you have H bonded with OH, that means H2O is what's formed.